Section 3.1, we're going to look at scatterplots and describing correlation. All right, so most of what we've been looking at has been one variable. Now we're going to look at two. Got to make sure we can classify them as either a response variable or an explanatory variable. In science terms, the response variable would be the dependent variable, and the explanatory variable would be the independent variable. Warning, all right, and thing to remember, a lot of times when we're looking at these studies, they are trying to prove that one variable causes the other one to change. All right. Sometimes they're trying to prove that, but we have to make sure that we aren't assuming causation. Okay. So the graph that we're going to be looking at is a scatter plot. This is nothing new. You have seen this before. Okay, you're going to have to draw scatter plots. Okay, so you got to make sure that we label the axes with units and what we're talking about. The explanatory variable goes on the x-axis and the response variable goes on the y-axis. Make sure that you have a scale on the axes, and then plot the individual data points. You can also use your calculator to make the graph and then draw a sketch of that on your paper. But you got to make sure when you use a calculator that your axes are both labeled and scaled. So we can't just kind of copy the general sketch from the calculator. Okay, that's why I would use that trace feature so you can actually see each individual data point. Okay. Describing a scatter plot, there are four things that you need to describe when asked to look at a scatter plot. Okay, direction. So the direction of the associations, either positive, negative, or none. Okay, this is not like a new concept. If the graph is going up, it's a positive association. If it's going down, it's a negative association. If we can't really tell, then there's no association. Okay, so we'll look at some examples. So this graph here would be a positive association. It is generally trending up. This one would be a negative association. It is generally trending down. And this one doesn't really have a trend, so we say that is no association. Form, we're going to either call it linear or nonlinear. Sometimes you'll see the word curved used. Okay, so does it make a straight line or does it curve? Strength, we're going to call it weak, moderate, or strong. Okay, and we'll also look at the correlation coefficient R to kind of give us a better idea of which one of those words we should pick. And then unusual features. So if there's an outlier, if there are two separate clusters, things like that, we want to point out in our description. Okay, you also have to make sure that your descriptions are written in context. Okay, so we should be talking about whatever the variables are. Don't just use numbers. Okay, talk about it in context of the problem. So here's an example. We have a scatter plot where we have the percent of students that take the SAT and then the mean math score. All right. And so this would be an example description of this scatter plot. So it addresses the direction. This is a negative association. It addresses the form. This is a slight curve. The strength, we would call this moderately strong. It's not really perfect, but it's pretty good. And then unusual features, we got kind of two distinct clusters with this gap here in between them. Okay. So scatterplot can show us that, and then we also can find something called correlation, which is R, which can give us like a numerical descriptor of the strength rather than just trying to say weak, moderate, or strong. Okay. The notes that we have to take is that it has to be between two quantitative variables. All right. Otherwise, we can't use R, and it has to be a linear relationship. So if the graph is curved, R is not helpful information. Okay. You may have remembered talking about R in Algebra 1 or Algebra 2. Okay, it's always somewhere between -1 and +1. It can tell you the direction. If it's positive, then the R will be a positive number, and if it's negative, the R will be a negative number. -1 and +1 would be perfect correlations, all right, where the points are exactly in a straight line, the closer, that rarely happens, so the closer we are to either 1 or -1, the stronger the relationship is. So like 0.9 is a really strong relationship. When we get closer to 0, the relationship is weak. Okay, so here's some examples. Like this has no correlation. This may be slightly negative, so we have -0.3. All right, whereas like this one is a super strong negative correlation that very clearly makes a line shape, so that would be -0.99. Okay, we got to be able to interpret correlation, and so we have this interpretation sentence. Okay, so the linear association between, we're going to talk about the x context, so our explanatory variable, and then the y value in context. So in this case, student absences and grades is either weak, moderately, or strong, or weak, moderate, or strong, and then is it positive or negative, so that we're addressing all of those things in our interpretation. So here's an example. We have payroll and number of wins for Major League Baseball teams. We can call this a linear association, and they gave us a value of R of 0.613. So the linear association between payroll, my X number, and number of wins, my Y-axis number, is moderately strong and positive because it's going in this direction. Okay. Some things that we need to remember about correlation. Correlation does not imply causation. Okay, correlation does not equal causation. Correlation is just a relationship. We can't say that one causes the other. So for example, this meme, ain't nobody got time for that. Okay, the popularity of this meme, how often it is searched for and used, matches really, really closely with the number of nursing assistants in Alaska. Okay, I don't think it is reasonable to say that people searching for this meme causes causes Alaskan hospitals to hire more nursing assistants. It's just some random coincidental correlation. There is no causation here. All right, correlation does not measure form. So it does not look at like, oh, this is a really strong curved relationship. Okay, you have to look at your scatter plot and make sure that it makes a line before you look at R and get anything useful from that information. Okay, it can only be used to describe linear relationships. Here's a graph. That is a very strong relationship, but it is curved. And so if you were to get the R value, it would be 0, even though there is a very clear pattern here because R cannot measure curved relationships. So it's only for linear relationships. Okay, and then correlation is not a resistant measure of strength. So if you remember from the beginning of year, we talked about mean and median, where the median was resistant to outliers and the mean was not. Okay, correlation is not. So here's a graph. Over here, we got this really strong relationship and then this random outlier. So if we put all of these points together, we get a R of -0.13, even though these are going up because of this outlier out here. But if I take this outlier out, then my correlation is 0.72. So that's a huge change. We went from a weak negative correlation to a strong positive one by removing one outlier. Okay, so outliers have a huge effect on R. All right, this is the equation for correlation. You most likely will not be asked to calculate it like with this equation. I just want you to see what it looks like so that it can help you understand some of the characteristics of R that we're about to talk about. Your calculator will give you this, or the problem will give you this. So it's not like you need to know how to use this formula. I just want you to see how it's the x value minus the mean of all the x values divided by the standard deviation, and then the same thing for y. Okay, so some things about correlation. All right, these are characteristics about it that you need to know. Both variables have to be quantitative. We talked about this, okay, because again, in this formula, I can't really put in categorical variables here. Okay. Second thing is it makes no distinction between explanatory and response variables. Okay, look at this equation. I have x minus x divided, and then I'm multiplying these numbers. So if I switched my x and y values, it wouldn't make a difference because multiplication, the order that we multiply things, does not matter. All right. It does not change when we change the units of measurement, because we end up dividing by standard deviation, which means we do something called standardizing these values, so the units of measure don't matter. And correlation does not have a unit of measurement, okay? It's just a number. It's a number between -1 and 1, but there's no unit for R, okay? So here's a scatter plot that we have between the height of people and the number of steps it took them to get down a hallway. All right. Explain why it isn't correct to say that the correlation is negative 0.0632 steps per inch. Okay. So this is what we just talked about. Correlation does not have units because it's used standardized values. What would happen to the correlation if we switch these, if we use number of steps as the explanatory variable and height as the response variable? Nothing, all right, because changing the order that we multiply numbers doesn't matter, so there is no distinction between explanatory and response variables. And then the last question, what would happen to the correlation if height was measured in centimeters instead of inches? Nothing, because again, we're using standardized values, so changing the unit does not change correlation. All right, and that's it for 3.1, guys.